What is binary search tree? Binary search tree has the property that every node have at most two children, and the right side of that node should be the larger values. And due to this binary search tree, we can decrease the time complexity because to search an element, we can eliminate half of the remaining nodes that are presented in that uh, binary tree. Now let's see the example that here 40 is said to be the root node and these are called as intermediary nodes and these last four are called as leaf nodes. How we can say that these are intermediary nodes, these are leaf nodes and these are root nodes? If there is no childs for those nodes, those are called as leaf nodes. For 25 there is no node and for 35 also there is no children. For 45 there is no children, 60 there is no children, so these are said to be a leaf nodes. And the whatever the element that is present at the top of the tree, that element is called as root node. So here 40 is called as a root node. And what are the elements are present at remaining levels? Those are called as intermediary nodes. Next, we will go and see how to insert an element. How the insertion is going to be takes place. Here, if we take 50 as an element, the insertion property, like how we discussed it before, like that, here initially there is no element, so insert 50. Next, later insert 80. To insert 80, we need to check the condition that here 80 is greater than 50, so we need to insert it right side of the 50, so it is inserted right side of the 50. Next, insert 30. Here 30 is less than 50, so here 30 less than 50, so insert left side of the 50. Now add 20. 20 is less than 50, so but there is an element at the left side of the 50, so it is checked to this 30. There is no element at 30, so it will insert it that left side of 30. Now insert 100. Here it will check with 50. 100 is greater than 50. Now it will move to right side of the subtree and there is an element 80. Again it will check with 80. 100 is greater than 80. So 100 will be inserted left side of the 100. Right side of the 80. Next 40. Compare 40 with 50. 40 is less than 50. So it will check in the left subtree. Here 30. 30 is compared with 40. 30 and 40 greater than 30. So insert 40 right side of 30. This process is continue until we find an appropriate position to that new node. Next, let illustrate with an example that here inserting 100 less than 50. The traversal of right subtree is here this is the logic that we are going to be implementing. Here item is less than root dot value. That means item here is that 100. Element to be inserted is 100. So 100 is the item and root dot value is 50. So this is greater than item is greater than 50. So it will check to the next nodes. Root equals to root dot right. That means it will move to here. That means it is now pointing to the 70. So again the item 70. Item means 100. 100 is greater than 70. Condition is satisfied. Again it will check to the right side of 70. There is an element 90, so again it will point that 90 has a root node and item is compared with the root node, that means 90. Now root equals to root dot right, means there is no element at right side, so the 100 will be inserted right of the 90. This is how the insertion is taking place. Let's see how to write the code. This is how the code. If the root is none, it will directly returns the value that what we are passing. If the value is greater than less than the root value, then it will be insert left side of the root, else it will insert right side of the root, returning the root value as we know that. Next, let's see how the deletion is going to be takes place. Removing the deletion is, there are three cases in the deletion. That is the node, if it is a leaf node, if we are deleting it is a leaf node, if the deleting node has at least one child, if the deleting node has the two children. Now if the node has a leaf node, then we can simply remove it, else we need to replace with its child. That means we will see example later. Just first basically understand the concept. Here the node to delete has two children. The node in order predecessor or in order successor is replaced with the deleting node. Let's see how it is going to be traced out. If the leaf in BSD is a leaf node, now deleting node is 20. So directly we can delete the 20 from this node. There is no issue with this. If the node has a single child, that means we are going to be deleted. The node is 70. So replace here this 80 is directly connected to the 50. That means whatever the node that we are deleting, the attached the child of the deleting node to the parent of the deleting node. Then we will insert 80 to the 50. Now after deletion, the tree looks like this. Next, let's see how to delete the node with two children. That is the case 3. In this example, we are going to delete the node 40, which is having the two children, that is 20 and 60. Now we can replace the 40 with in order predecessor or in order successor. That means we can replace the 40 with largest element in the left subtree or the smallest element in the right subtree. That means we can replace 40 with 30 or we can replace it with the 50. This is an code for deleting the node in BSD. For finding the minimum value node, here check, let's take the current element as a node, while current dot left is not none. That means there is an element at left side, then we will move to the left side, then we will return that node whatever that present in the left side. That means every time the left side nodes are the smaller than the root node, so we are going to be check the left side to calculate the minimum value of this node. Next, how to delete the node. Root, now we are passing the root value and what is the value that we are going to be deleted. If the root is not none, if the root is none, that means there is no element, then it will return the root. If there is an element, then it will check with the value that is presented at the root value. That is greater than, then it will move to the right. If it is less than, then it will move to the left. If there is the left, then it will delete the value that is presenting in the root dot left, comma that value it will be deleted. If there is an element at right, then it will delete that element that is presenting in the right, and whatever that value is there, that will be deleted. Else, if this is not satisfied, that means here this is only the case with single node and like that. That means with if it is a leaf node, if it may be the contains a single child also, no. So for that case, here we are writing the logic that if the left side is none, then return whatever the value that is presenting at the right side, that will be going to be written. If it is returning the left side of the node, that means there is an element at the right side, then it will return the left side. Now here we are taking the temp as a variable. That means we are storing the value that what we are passing at here, that is storing in this value temp, that is minimum value. Here the root dot value means whatever the value that is presenting is equals to temp value. Now here we are assigning the value that is presenting in the temp value, that is going to be presented at the root value. And if we are going to be deleted the right side of the root value, so we are deleting root dot right comma value at that value. Later we are returning the root. Next, see how this iteration is going to be takes place in visually. Here deleting 60 initially, so we are, this is a leaf node, so we are directly deleting a 60. Here deleting 50, so 50 is contains one child, so we need to swap this. That means we are connecting the parent node of the 50 with the child node of the 50. So swapping 20 and 50. Later we are removing this 50 in this step. Then the root becomes like this. The tree became like this. Now again we are taking the initial tree. Now delete 100. To delete 100, we can insert in order successor, or we can take in order predecessor. Here we are taking in order successor of 100 is 120. That means we are inserting the smallest element in the right side of right subtree. of that particular node. So 120 is the in-order successor. Now swap the 100 and 120, then delete the 100. Now the tree became like this. This is how the deletion is going to be takes place. Now find the height of the node. Actually, what is meant by height? It means the length of the longest path from the node to the leaf node. Here, this is the leaf nodes, right? For finding the height of the 13, we are going to be checked from depth wise. That means this is 1, this is the height of 0, this is the height of 1, this is the height of 2, this is the height of 3. That means height of the 13 is 3. Now check how to write the code for the height of the node. Here if the root is none, it will return -1. Otherwise, it will move height of the left subtree. And again it will move height of the right subtree. That means we are taking the maximum of both and we are incrementing by 1. That is how we are calculating the height of the node. Next, see what is a level of the node in BST. This is the distance from the root node to the particular node. That means here we are calculating every node, we are calculate the level from the root node. For example, for 40 we need to calculate it from the root node. That means here it is 0 level, 1, and the 40 is at the second level. How we are going to be done? To start the root and traversal down the node, incremented the level at each step. Okay. Now see an example, code. If the root is none, return 0. That means there is no element. If the root value equals to node dot value, then return level, at what level it is going to be present. For down levels, self dot find level is another function. That is, this function name is find level. We are passing the left side root node and node value and level plus 1. Why we are adding the level? The element at wherever the level that is presenting is also considered as one of the levels, so we are adding +1 to that level. If it is not equals to 0, then return down level. That means we are finally returning this, the level that is presenting at the find level, comma root dot right, comma node, comma value plus 1. Check if the node is a leaf node or not. To determine how we will check, if the element doesn't have any right and left subtree, then we will consider as a leaf node. For this, here in this example, -4, 9, 7 are considered as the leaf nodes because there is no subtrees or no children for these elements. Then these are called leaf nodes. The algorithm for this is, if the is leaf is the function name, we are returning that if left node is none and right node is none. That means wherever that the node dot left is none and again the node dot right is also none. That means there is no children for that node. Then we are returning that value as a leaf node. Let's see what is in-order predecessor and in-order successor of the given node. What is in-order predecessor? The maximum value of the left subtree is called in-order predecessor. What is in-order successor? The minimum element in the right subtree. That means, for example, let's take an example has 33. The in-order predecessor of 33 is, that means we need to check in-order predecessor has a left side of the node. That means we are going to be check this subtree. In this subtree, what is the largest value that is presenting in this node? That is called in-order predecessor. That means here 25 is the largest value, so this is called in-order predecessor. And for calculating the in-order successor, we need to check the right side of the tree. That means here we need to find the smallest element in the tree. Where 34 is the smallest element in this tree, so it is considered as the in-order successor. Now see the code for this. For finding the minimum value node, we are passing the node. That node is assigning to the current. If there is no left, then we are returning the value current dot left. That means value we are returning. If there is a maximum node, to calculating the maximum node, we are passing the node again. That node is storing in the current variable. If the current dot write is not null, that means there is an element at right side, then we are replacing the write value to the current, then returning that current, then we are finding the root. Here why we are checking for find minimum value only the left side and for maximum value we are right side, because in the BST it follows comparatively with root node, the elements the presenting at the left subtree are the smaller than the root node. So we are for finding the minimum value node, we are checking it side left side. For finding the maximum nodes, we are checking it at the right side. Now check how to search in BSD. Searching is takes place by if the key matches, then it is okay, it will returns that node. If the key doesn't matches, then it will check the condition, is it greater than or less than. If it is less than, then it will check the left subtree. If it is greater than, then it will check the right subtree. Now see how the code is to be going, how this is going to be illustrated. Here the item that we are going to be search is 60. Here item is less than the root. Here root value is 50. So item is checked with the 50. Item is greater than the root. So it will move to the left side. Again the root is pointing to the 75. So 75 is greater than 60. False. 75 is less than 60. Sorry, 60 is less than 75. That means we need to check with the left side of 75. So item is 65 and the root value is also 65. This means it founds an element has 60. It returns the value 60 to that main function. Now see how the code is to be going to be right. Here search is a function, we are passing the root value and what is the element that we are going to be searching for. If the root is none or the root value is equals to key, that means there is no root or there is an element key, there it founds an element key, then it is returning the value that is presenting at the root. If the value that is present at the root is less than key, then it returns, then it's saying that check right side of the tree, then it is going to be check right dot root dot right comma key, else it is returning left side. That means if the root dot value is greater than key, then it will search left side. That means in BST each and every process takes place in recursive manner. So this is how we are going to be right. Um, that is what about the BST. Thank you for watching this.